we backed up a couple of videos ago, one of the solutions that you saw that I came up with was that this result equaled that by using DeMoivre's theorem. And what we could say is that this result here, I could say, is the sixth complex cube or root, distinct root of that particular term. So what I want to try to unpack to you a little bit is this idea of distinct roots or distinct nth roots of particular terms. And this might be kind of heady a little bit, so try to pay attention a little bit because I love the result. The work getting there, it takes some effort to try to follow along, but I love where it ends up at. So I hope you kind of get the idea as well. And the idea is talking about that when we look at powers of these complex polar numbers, that every one would have, for example, 2 distinct square roots, or 3 distinct cube roots, or 4 distinct fourth roots, 5 distinct fifth roots, and so on. And all those points, if we were to graph them out, will be spaced on a circle equal distance from each other around that circle. And that's what I find is fascinating. And so we can look at DeMoivre's theorem by looking at this idea where I want to find a distinct root. And it follows this idea that I have listed there. So I'll show you an example of how it works out. We have 2 versions, one in radians and one in degrees. And basically what we're doing is we're taking whatever root we're looking at and dividing it through by that root to find its distinct root. So I have this value here, 16 cosine 120 degrees, I sine 120 degrees. And I want to find its 4 distinct roots. Basically, it'll tell me that I'm looking at its 4th root, and it has 4 distinct complex roots. So if I look at n equals 4, in this case, let's just unpack that. Okay, first I noticed that it's in degrees and not radians. So I'm going to have this idea where I'm always adding some 360 degrees to the number. And these are for all k's up to n minus 1. So I'm going to be looking at the values of 0, 1, 2, and 3. Because n minus 1 is 3, 4 minus 1. So I'm only going to check 4 places because I have 4 roots, complex roots that I'm interested in at this time. So let's rewrite this in terms of this type of an idea. And I'm going to do it 4 times for 4 different places. All right, you tracking? All right, so let's look at z to the 0 root, or first root. So that is 4 square root of 16 cosine theta, which is 120 degrees, plus 360 degrees times k. K in this type is 0. All divided by n, which was a 4, plus I sine of the same amount, 120 degrees, and so forth. So let's figure out what that amount is. The 4th root of 16 is a 2. Cosine 120 degrees plus 360 times 0 is 120 degrees. 120 degrees divided by 4. 120 divided by 4 is 30. So there I found 1 distinct root of this number here, and I want to find 4 distinct roots. And so I know there's going to be 4. So that was the first one. Let's look for the second one. So let's set it k equal to 1. So I'm looking for its next one. So I'll be 4 root 16 times cosine 120 degrees plus 360 times 1 this time, all over 4, plus I sine of the same argument, whatever that argument is. So 4 root 16 is a 2. Cosine 120 plus 360 times 1 gives me 480. 480 divided by 4. (120 degrees) plus I sine 120 degrees. All right. Same process for Z3, Z2, 4 root 16 cosine 120 times 360 times 2 all over 4 plus I sine, that equals 2 cosine 360 times 2 is 720. 720 plus 120, 840. Divide that by 4, gives me 210. And the last one, the last root, I know there's 4 of them. First one, second one, third one, fourth one. I'm looking for this, and it's fourth roots, so it's got 4 distinct complex roots. So wait for it, we're still getting there. So I'm going to have 4 root 16 times the cosine of 120 times 360 times 3 this time, all over 4 plus the sine argument, 360 times 3. You guys probably know these, I don't. 0, 8, 1, 180. Add 360 to it. 1440. Divide that by 4. See if I made a mistake somewhere. 360. Oh yeah, 120 times 3 is 360. I'm getting rid of one of them. So 2 cosine 360 degrees plus I sine 360 degrees. Now what's cool, that if I plot these all out, it's not 360, my notes say that's 300, so I made a mistake here. $360. I'll catch my mistake here in a little bit, but this came out to be 300 degrees. I'm sure I made an error over there somewhere. So 360 times 3, I'm curious. 360 times 3, 0, that's an 8, 9 at plus 120. Plus 120. Divide that by 4, that gives me 300. All right, all is all right with the world. So I have a complex root here, complex root there, complex root there, complex root there. They're all distinct. And what's cool, that if I were to graph this out on the complex plane, its radius is 2, so it's all, so I have some circle with a radius of 2. These 4 points, I know they exist on the circle, and I know that they're all equal distance from each other on the circle, which is kind of cool. So at degrees of 30 degrees, I have a point there. That's 120 degrees, I have a point there at 210 degrees, and then a point there at 300 degrees. So there are the 4 points. Be better if I kind of drew it in different colors. Then you kind of see where they're all kind of at. And they're all equal distance on the circle, which I find fascinating. It's almost like when you imagine magnets. And magnets, if they're all pointing in the same direction or opposite each other, they all kind of find an equilibrium. They all exist at the point that's the closest and the farthest away from all the other points on the circle. So that's why I look at these points, is that they're all existing in the place where they have to be, and they're all equal distance. And that's cool. We could solve this for a 3, where n equals 3, or n equals 2, n equals 5, and so forth. And so this is a wonderful opportunity that's going to open up a lot of future ideas as you continue to explore your chemistry and your physics and so forth, or just for your own curiosity.